This is a very apropos topic to start out the day with in light of the DMIST trial, and we will be talking about the DMIST results specifically toward the end of the lecture. But before we start, how many people have digital equipment in their practice? Well, you're way outside the norm because countrywide, across the United States, about 7% of mammographic installations are currently digital. So the implications of going to digital are significant, and we'll talk about that as well. When we think about mammography in general, we have to keep in mind the goal as we're thinking about such a huge endeavor as completely switching over our equipment. Clearly, the idea is to produce detailed images of the breast in order to help us detect breast cancer earlier and thus afford the individual the possibility of a cure. So we have to go back and think a little bit about how X-rays are acquired in the analog world, and this will be brief, I promise. The X-ray photons passing through the breast will strike the cassette which contains a screen film combination. The phosphor screen will then absorb those X-rays and output light in a process that's called scintillation. And that will develop a distribution cloud within the cassette, which is proportional to the amount of photons striking the cassette at any point. The technologist then places the cassette in the processor, and the image is transferred for a film for the radiologist to interpret. So when we look at that construct, we can see that the analog film is serving as the vehicle for the acquisition, the display, and the storage of the image. Now, in many ways, this is a highly efficient process. It's inexpensive. The film itself is extremely high resolution. I love it when the residents say they'd rather read MRI or CT because it's very high res. Well, there is no higher resolution examination in radiology than mammography. It holds an enormous amount of information in a very compact package, and its display is quite straightforward. But we all know that it has significant disadvantages as well. And it's really because the film is serving both as the detector and the display medium that those limitations come to bear. The technologist needs to acquire the image over a very narrow range of parameters so that we will be able to interpret the image. And that is technologically challenging. If the image is acquired in a somewhat suboptimal way, there's not a lot you can do on the back end to make up for that. Once the film is developed, its display parameters cannot be altered. You can look at it with a bright light, but that's about it. The film, of course, represents the only record of that study. If it's lost, there's nothing you can do. And the storage requires space. And as we're faced now with hospitals wanting to compact their spaces, to devote the majority of their spaces to patient care, this is becoming a challenge, and many institutions are having to move their film storage off-site or get away completely from film storage, another value of digital imaging. So when we talk about digital mammography, exactly what are we talking about? There are different approaches. The first is digitization of analog images. Now, certainly this is not what most people mean when they talk about digital imaging. There is going to be some loss of information, some introduction of noise, and again, you'll be set with what the parameters were of that analog image before you started. So this is not the ideal. Now, you could do some digitization of information using an intermediate or a hybrid receptor. That is the Fuji system that is under development, and we'll talk specifically about that. But I think when most people say digital mammography and digital imaging, they really mean full field digital acquisition on a solid state digital detector. Well, digital imaging is really of value because it decouples those functions that we talked about, the acquisition, the display, and the storage, to allow you to optimize each one individually and make it as best it can be. Well, what is this digital imaging? Well, if we look at the detector, it is going to be divided into individual picture elements, or pixels, and that essentially constitutes a grid. As the X-rays pass through the breast and strike this digital detector, the number of photons striking at any one point is going to be recorded numerically by the detector and then passed on to the computer. And so here we can see a bunch of numbers, hence the name Digital. This really represents the number of photons striking the detector at any picture element. This numerical information is what is going to be stored by the computer as what it perceives as your image. Now, we can't interpret numbers, so we have to apply a grayscale. And we apply that grayscale assigning an attenuation value for every digital number. Now, if I have a given set of digital numbers and I transmit an image to my colleagues here at NYU and they apply the same grayscale, we will be looking at the exact same image. That is one of the advantages of digital, the transmission of the image around the world to allow for simultaneous consultation and remote interpretation. So here we're applying our grayscale. Now we have what we can interpret as an image. Well, as we look at the different vendors and we try to assess whether switching to digital is of value for us and how will we pick amongst the various manufacturers, we have to consider a couple of things. Certainly, everyone understands that we need high-resolution images. But what is high resolution? Well, it really has two different components. There is spatial resolution, which I think we're all familiar with, but there's also contrast resolution. The spatial resolution is aiming to capture the fine detail of the image, but the contrast resolution is critical in mammography. Because the background information, the breast parenchyma, is so similar in attenuation to the object of interest, the tumor, we need to have excellent contrast resolution to be able to discern between very close levels of attenuation. And that is something that I think that we haven't had to think about very much in the analog world. Well, let's look at some spatial resolutions as we compare different imaging modalities. As I said, screen film mammography, incredibly high resolution, coming in at somewhere between 17 to 20 line pairs per millimeter, very high. Well, how about a digital detector with 100 micron pixel size? That is the General Electric detector. That has a spatial resolution of about 5 line pairs per millimeter. Suppose we go down to one of the smallest pixel sizes available, the 50 micron pixel size, which was the Fisher detector system. That is still only 10 line pairs per millimeter. If you just looked at that data set, you would say, why would I ever consider switching to digital? What possible additive value could it have? Well, the key is that we cannot look at this spatial resolution in isolation, because it is true that digital mammography has significantly lower spatial resolutions than screen film mammography. But that decrease is absolutely offset by the huge increase in contrast resolution afforded to you by the modality. And so these things have to be looked at in concert for you to understand the type of image that you are going to get from your digital mammographic system. In both the fatty breast, and these are digitally acquired images, the heterogeneously dense breast, and the extremely dense breast, all digitally acquired images. Well, as we start to develop a conversation with the manufacturers, we have to be savvy to what they're going to try and tell us to convince us to buy their equipment. When we think about spatial resolution, it's important to recognize that if I'm imaging a phantom that consists of metallic objects embedded in a gel, that my inherent contrast, the difference between the metal and the adjacent gel, is going to be almost 100%. And so the mammographic equipment will not have to perform exceedingly well to be able to show those two objects as distinct. As I bring the contrasts closer together, however, as would be analogous in the breast itself, if I don't have adequate contrast resolution, I will not be able to discern two objects as unique. And so looking at a vendor's specifications in terms of spatial resolution, it is critical to understand how they came to that determination, whether it was based on phantom work or whether it was based on native tissue work. Let's look at this schematically to try and understand this situation. If I have a mammographic system that has excellent spatial resolution, I can have an object here, take an image, and discern it as two separate unique elements. But if my spatial resolution is not particularly good, and I now take an image, these two objects will blur together, and I will be unable to identify that they represent two unique elements due to insufficient spatial resolution. Well, now let's take a system that has exquisitely good spatial resolution, but not very good contrast resolution. Here I have my two unique elements embedded in a background that is close in attenuation to the elements themselves. As I take the image, all I will see is this blob that represents the background noise. And because my contrast resolution is not good enough to discern the differences between these two things, it will not matter how good my spatial resolution is. I will not see the elements at all. Suppose now I have a third system. It has pretty good spatial resolution, but it has excellent contrast resolution. Again, my individual elements are close to each other in contrast attenuation from the background information and close together in space. When I take my image, I will indeed see those elements. Yes, they may not be 100% resolved with respect to each other because of the limitations of the spatial resolution, but I will see them and be able to initiate that workup. This is essentially what our currently available mammographic systems do. So spatial resolution cannot be evaluated in the absence of information about the system's contrast resolution. So now let's talk about some of the specific digital technologies out there and recognize that when we're talking about different approaches to manufacturing the digital detector, this is the proprietary information of the vendor. They all have to be different because this is what is patentable. So each vendor's approach is going to be different, and it will therefore have different pros and cons associated with it. We'll talk about the slot scanning approach, which is the background of the Fisher detector, the thin film transistor array, which is the General Electric detector, Chargedcouple device approaches, which were the original low-rad detector, no longer in use, amorphous selenium flat plates, which is the current selenia from Hologic, and the storage phosphor system that I alluded to earlier, a hybrid approach from Fuji. Now let's look at the first one, a slot scanning design, which is the Fisher detector. What we have here is a pencil-thin beam of X-rays that is going to traverse the breast in a uniform way, exposing only a very limited quantity of breast tissue at a time to the X-ray beam. Now, because it's traversing the breast and only imaging part of the breast at one individual time, the acquisition will be slower. Because each individual slice will be related to its neighbors, that decreases any introduction of motion artifact. But this construct is very effective in eliminating scatter, so much so that this is the only system that does not utilize a grid. The lack of a grid means that the dose is extremely low, and those are the advantages of this system. It also gives exquisitely detailed images. The thin film transistor array is the General Electric approach to a detector. Cesium iodide crystals, depicted here, are grown on a thin film of amorphous silicon. On that silicon, thousands upon thousands of tiny transistors are bonded, and each one is individually wired to an XY grid to record its information. In this construct, the X-ray photons are going to come down and be converted by these cesium iodide crystals to light. That light will then travel down the crystal and be detected by the transistor array and converted to electronic energy. The energy at any one point, remember at each pixel, will then be read out by an individual transistor according to all of these tiny wires. Now you can see that this is an incredibly intricate detector design, and that explains why the GE system has a small field of view. It is very complicated to develop this any bigger than it currently is, and that has been the challenge in General Electric bringing a larger field of view detector to market. It's just simply the construct of their design is quite complex. Let's look at the charged couple device approach. This was the original detector on which LORAD got its FDA approval. Here we have a fluorescent screen which is going to function very similar to a film screen combination. It's going to absorb X-ray energy and convert it to light. The light is going to travel down these fiber optic tapers until it reaches the charged couple device where it will be stored as electrons. This is exactly how your digital camera works. Then the charged couple device will read out the electronic information, and that will be proportionate to the number of photons that struck at any one point. Now, because these charged couple devices are all made individually, they can be tiled to form a detector of any size that you are interested in. And this is the original tiled CCD digital detector. Now, you'll notice that all of these approaches essentially used the same theoretical system. They took the X-ray energy and converted it to light, and then converted that light information to electronic information. Now, we know that when there's an intermediate conversion to light, you're going to lose some of the spatial resolution and the information detail. Why is that? Think of it as a flashlight beam. You know that as the beam spreads out, it becomes more broad. Well, similarly, as light spreads within the detector, you develop this line spread function, introducing a minute amount of blur. And so manufacturers were interested in eliminating that intermediate conversion to light. And that was really the impetus behind developing the direct conversion digital detector. Here, you're going to use a photoconductor, an element that can directly absorb X-ray information and cause a chemical change in the detector that will be read out as electronic information without an intermediate conversion to light step. And one of those elements is amorphous selenium, which was really the technology involved in Xerox and zero radiographic imaging. Here, the X-ray photon will strike the selenium plate and cause a change in the selenium plate, which will develop as an electronic charge and be read out as the detector. There will be no intermediate conversion to light, and so all of the information that was acquired by the X-ray photon will be captured by the computer. That is the basis of the development of the flat plate amorphous selenium detector that is now the technology implied by LORAD and by Siemens as well. Well, suppose I'm interested in digital technology, but I understand that it's going to be incredibly costly to switch over. Is there any possible intermediate solution to me which would be analogous to a CR imaging system? Well, yes, Fuji is developing that system. It is a hybrid technology that allows you to acquire the exposure in your standard analog mammographic acquisition machine. How does it do that? There's a specialized cassette, and rather than having a film screen combination, that cassette is going to have an embedded europium activated compound. That's just a fancy term for saying there's an element that can be raised to different energy level states, so that when X-ray photons strike that cassette, they are now going to raise the europium at any given point to a different level of energization. Then you take that cassette with its activated europium and you put it in a specialized developing system, not your standard film processor, but now a laser system that will actually release that latent energy that was caught by the barium and europium compounds and actually release a quantity of light that's in proportion to the number of X-rays that hit at any point. And that will be recorded as your digital image. So it's sort of half digital, if you will. But the major advantage, it allows you to keep your analog equipment. It is not currently FDA approved, but the company is working very hard in that direction. So now let's look again at a summary of some of these different detector approaches. We have General Electric that has a resolution, which is depicted as the pixel size of 100 micron, and a given field of view that's analogous to a small cassette. The LORAD selenium has a 70 micron pixel size because of its direct light conversion. And it also has a larger field of view because it's easy to bond the amorphous selenium to any size plate you want. The Fisher detector, the slot scanning system, has pixel sizes that are incredibly small, 50 with a spot size of 25, very fine resolution, but a smaller detector size. The Fuji system, because it is cassette-based, comes in different sizes, just as would your screen film cassettes. Now, all we've talked about is the acquisition of the image. We have not talked about storing that image for us to interpret with our grayscale application. Well, in order to apply the number of dynamic range elements that we're interested in, we need to use a significant amount of computer memory. And typically, 12 or 14 bits of memory are used at each pixel to quantify that information. What this means in plain terms, mammographic data sets when digitally acquired are huge. And this is a challenge for our archival colleagues in order to store our images, to get them back to us quickly, and have them available in a timely way. Well, how much information are we talking about here? Well, how about for the General Electric detector that has 100 micron pixel size? Well, that will basically translate to 100 pixels per centimeter. We know the size of the detector, so we can calculate that that's about 4.4 million pixels that are present on the detector. If we now apply the 14 bits of memory per pixel that are used, we will come up with about 7.6 megabytes of information per image. Well, now let's think of the selenium detector, the low-rad detector. It has a smaller pixel size and a larger field of view. And what that translates to is almost 15 million pixels present on that detector. And again, if you then encode it with the memory and grayscale that you need to give you that beautifully attenuated image that you're looking for, you're talking about 26 megabytes per image. That means a standard mammographic examination of 4 images will come in at about 100 megabytes. And now think about doing 100 women a day. This is an incredibly huge amount of information, and really the translation to digital from the analog world really rested in part upon 2 things: the development of the full field digital detector and the ability to handle this amount of information in an efficient way. Well, now let's get on to the better stuff. We know how the digital detector works, but is it any better than film screen? Is it indeed time to switch or not? Well, let's look at some of the clinical studies. The first major study that came out was from Carl Dorsey and John Lewin, and they directly compared screen film acquisition to digital acquisition. In their study, they diagnosed 35 cancers, and I'd like you to look at these cancers. 12 were diagnosed by both modalities, 9 were diagnosed by digital only, and 10 were diagnosed by screen film only. So yes, indeed, there was no statistically significant difference between digital and film screen for the detection of breast cancer, but what's often lost in that translation is that a significant number of cancers were detected only by one modality or the other, and we're going to come back to this later. They did note a statistically significant difference in their recall rate, with digital affording a lower recall rate, but noticed that their recall rates were slightly on the high side to begin with. Now, in Scandinavia, they attempted to duplicate these studies from Lewin and Dorsey. Well, they got about 4,000 women who again underwent both imaging modalities, and they found the same thing: no statistically significant difference in cancer detection between screen film and digital. Their recall rate was slightly higher on the digital modality, but again, look at how low the recall rates were in Scandinavia, somewhere on the order of 3 to 4%. They expanded on this with a population-based study that is similar to the mammographic trials that went on 30 years ago. Here in this population-based study, they enrolled about 25,000 women. And what they found here again was that there was no statistically significant difference in the cancer detection rate. Well, this is all a little bit depressing because we were hoping that the contrast resolution of digital mammography would afford us an incremental benefit in detecting breast cancers. But people postulated that perhaps these studies just weren't large enough. The benefit was there, but you needed bigger numbers to show it. Well, enter DMIST. The results of this large trial were released in September and have created a bit of a furor. Let's talk a little bit about the study itself. During a 2-year period, almost 50,000 women were accrued at 33 sites in the United States and Canada, and Mass General was one of those sites, and I'll tell you that I was one of the readers on the DMIST study. Did anyone else in the room interpret DMIST study? No. Okay, well, I'll be able to give you a little bit of insight just as a reader. I didn't analyze the data, I just read the studies. So women enrolling in this study underwent both digital and film screen imaging. 5 different systems were used, but the majority of women, the vast majority, were imaged on the GE system. We started out being a GE site, and then when the Selenia became FDA approved, we switched to being a Hologic site. The digital and film screen examinations were independently interpreted by different radiologists, and there was no attempt made to come to a consensus. One radiologist could not undo the other radiologist's interpretation. The readers rated the mammograms in 2 different ways. They used the standard BI-RADS categorization that we're all familiar with, but they also used a 7-point probability scale that I'll go into in a little more detail. The breast density was recorded in accordance with ACR standards, and we're all familiar with the BI-RADS categorization and the assessment of the breast density, but what is this 7-point scale? Well, the 7-point scale was presented to the radiologists, and they were asked to place each lesion at screening in one of these categories. Definitely not malignant, almost definitely not malignant, probably not malignant, maybe malignant, probably malignant, almost definitely malignant, and definitely malignant. Now, I'm not trying to be facetious here, but you can see over a period of 2 years, depending on whether you're tired, you're hungry, you haven't had your coffee, your ability to consistently apply some of these middle scores may vary somewhat. And the readers were all trained, but the training really consisted of tell me where you think the lesion lies on this scale. And the authors of the paper recognize and admit that the scale has never been validated. Further evaluation of any of the women proceeded on the basis of a recommendation generated by either modality, and the participants were asked to return for follow-up mammography in a year. Let's look at how they were classified as a positive. Participants were counted as a positive for breast cancer if they had a breast cancer diagnosed within 455 days of their initial study mammogram, 455 days. They were classified as a negative if they underwent a concordant benign biopsy or had a negative follow-up mammography at 1 year. Let's look at the results. A total of 335 cancers were diagnosed in the DMIST cohort. Very importantly, because this gets a little bit lost in the translation as well, the overall cohort showed no difference in the performance of digital and screen film mammography between the 2 groups. No difference in the overall cohort. Differences in performance were identified, however, in certain subgroups. Who were they? Women under 50 years of age, women who were pre- or perimenopausal, and women who were classified as having heterogeneously dense or dense breast tissue, BI-RADS categories 3 or 4 in the tissue pattern analysis. In those 3 groups of women, digital mammography performed significantly better in the detection of breast cancer. And their whole argument centered around this figure, Figure 1 from the New England Journal paper. And what we're going to look at here is the diagnostic performance in terms of an ROC curve that was developed using that 7-point malignancy scale from the radiologist. Now recognize that an ROC analysis attempts to incorporate both the sensitivity and specificity of the exam, or the interpreter's ability to call true positive results and true negative results. So this is a combined analysis as the ROC curve. Remember that 7-point probability scale. In order to do the analysis, you're going to have to make a cutoff point and determine what you will call a positive and what you will call a negative. So the authors decided to call these three, definitely not, almost definitely not, and probably not malignant, a negative. They decided to call the bottom four a positive. And so how the ROC curve will pan out will depend right here on the differentiation between probably not malignant and maybe malignant. Okay, now let's look at the curves again. Here, the dashed line is the digital performance and the solid line is the screen film performance. This is the overall cohort where you can see that there was basically no difference in the ROC performance of the interpreters. But look at these three curves, which are the women younger than 50, the dense or heterogeneously dense breast tissue, and the pre or perimenopausal. They look almost identical. That's interesting. Now let's look at the analysis that's more familiar to us. Let's look at the sensitivity and specificity of the examination, again, using the 7-point scale that the authors want us to use. Well, looking at all women, the sensitivity of mammography on the digital examination was 41%. The sensitivity on the film screen, 41%. Now, yes, they were not different at all, and so that's why there was no difference in the cohort. But is that what we expect as the performance of mammography? We know it's not perfect, but is it this bad with a sensitivity of only 41%? That's interesting. Women less than 50 years old. Again, some differences, but they are not statistically significant. Pre and perimenopausal women, some differences, not statistically significant. Similarly, women with dense or heterogeneously dense breast tissue, not statistically significant. So why is the ROC curve different? Because it's attempting to incorporate both the sensitivity and the specificity to look at the exam using that 7-point scale. Well, the authors conceded that this is not typically the way we look at a false positive versus a true positive exam. Usually, a cancer that develops within a year of having a negative screening examination is what we term an interval cancer, and that's what we will define as a false negative for that screening mammogram. Will not go out 455 days. If you pick up a cancer at the woman's next screening mammogram, we call that great. That's what we're in the business of doing. So this imposition of 455 days as the time frame in which a woman could develop a cancer was not in keeping with what most people would think of as a false negative. And so the authors conceded this and reanalyzed their data using the standard 365-day interval for looking at cancer development. When they did that, about a quarter of their cancers dropped out. They also recognized that BI-RADS categorization was more familiar to their interpreters, and so that might be a little more standardized, and they provided in a supplementary table the analysis of the data using the standard 1-year interval and the BI-RADS categorization. You had to dig a little bit to find it, but it was there. And so when we look at this now, we'll see that all women, in terms of the sensitivity and specificity of the exam using 1-year interval and BI-RADS data, shows a sensitivity of digital of 70% and film screen of 66%. Again, they were not statistically significantly different, but this is much more in line with what we would expect as the performance of mammography. How about these subgroups of women? In women less than 50 years old, there was an enormous difference with a p-value of 0.002 in the performance of the two modalities. This is hugely statistically significant. How about the pre- and perimenopausal women? Again, a p-value of 0.008, very statistically significant. How about women with dense or heterogeneously dense breast tissue? Again, a p-value of 0.02, statistically significant. What's interesting here is when you think back to the big picture of why we're doing digital mammography, what was our initial hypothesis? Why did we think digital would be better? It was really because we thought that its better contrast resolution would allow us to look through those dense tissues more efficiently to see cancers. And so if that is our theory, we would think that when we broke down the women who had the densest breast tissue, that would be the best performance of digital mammography. But in fact, it was not. And in fact, you were 10 times more likely to have your cancer diagnosed by digital if you were less than 50 than if you had dense or heterogeneously dense breast tissue. So that does not immediately make sense to us as we think about why these differences may be showing up. But one thing we have to recognize, remember those ROC curves all looked quite similar for the subgroups that showed a benefit from digital. Why is that? Well, in performing the subcategory analysis for the study, the authors counted the same woman in as many subcategories as pertain to her. So if we think about the women who were less than 50 years old, of which the total number wasn't given, but the mean age was, and we think about the pre- and perimenopausal women, well, most women who are under 50 are pre- or perimenopausal. How about the dense breast tissue? Well, most women who were less than 50 had dense breast tissue. And most of the women who were under 50 were pre- and perimenopausal and had dense breast tissue. Well, as it turns out, many of the women were counted up to 3 times in the analysis that was given out as the subcategories benefiting from digital mammography. So when we look at this paper and we talk about what are some of the points of discussion here, there was significant overlap in the groups for which digital showed a benefit. Can those subsets be broken down more independently to show what the independent contributions of age, menopausal status, and breast density are? That would be very interesting because, again, remember what I said at the outset, only about 7% of mammographic installations currently are digital. We're going to have to decide who is most appropriate to receive this imaging modality. The most significant difference between the two modalities lay between the women who are less than 50 years old. But it does not appear to be accounted for by, at least in total, by the differences in breast density. If it's not accounted for by that, what is accounting for that finding? That's not clear. If the area under the curve or the overall analysis for the cohort shows that there is no difference between digital and screen film mammography, and yet there's such a huge benefit for a certain subgroup, how is there not such a marked disadvantage for a different subgroup? And in fact, some people, in looking at the raw data, are starting to think that there was a disadvantage for digital in terms of women who had fatty breast tissue. Unclear, but it's hard to understand how you could have such a significant benefit from one subsegment and yet have the overall group be the same without someone showing a disadvantage. If we repeated that ROC analysis, the centerpiece around which they built their argument using the BI-RADS categories that were more familiar to the interpreters instead of the 7-point scale, would the results be the same? Remember, we looked at that 7-point scale and decided there was a somewhat arbitrary delineation there, and the 7-point scale has never been validated. But most importantly, think back to that Lewin study when I asked you to remember that 10 of the cancers were diagnosed only on film screen and 9 of them only on digital, with 12 being diagnosed by both. Can we perform a more refined analysis of the cancers that were diagnosed only on one modality or the other? If so, we might be able to improve digital technology. Because I'll leave you with this thought. This is just the overall pathology table from this New England Journal article, and this table shows the invasive cancers, and there were 85 total invasive cancers, of which, of the invasive cancers, 85 were diagnosed on both modalities, 35 were diagnosed on film alone, and 38 were diagnosed on digital alone. if you looked at these numbers, they're very similar to the Lewin-Dorsey data. Now, if I were a statistician from another planet, and I was just coming down and I read this paper, do you know what my overall impression would be and my recommendation would be? Women should have both, right? But the authors dismissed this as patently ludicrous. But I would submit to you that that's the strongest implication from the paper. So, when we talk about digital and DMIST, there's absolutely more to come. But perhaps the strength of the digital modality doesn't lie directly in its two-dimensional current depiction, but really in the fact that it now allows us to develop other technologies. What are they? Contrast-enhanced mammographic imaging. Because the digital modality can acquire and read out images so quickly, can we inject contrast and essentially perform an MRI using X-ray technology? How about fusion with other modalities, such as ultrasound or PET? And one topic that I'm going to talk about a little later in the morning, breast tomosynthesis. And so when we talk about digital, it's not just its inherent value as a platform itself. It's really our first opportunity to build additional technologies and modalities. And that's where I think the real value of digital lies. And I thank you for your attention.